Hey, Dust Counters, quick warning. On this episode, we recorded over a voice call on Discord instead of Skype like we usually do because Skype was acting up. But then Discord decided to act up and lag halfway through recording. So, somewhere around halfway in, we're going to sound kind of funny, but it gets better. On today's episode, orbital mechanics, and some science.
Orbital mechanics,
Welcome.
orbital mechanics, and some science.
Yes. On
Okay.
today's episode of End of Mission, we're talking about ISEE-3. I am Paul, the pressure-fed astronaut, and who are you?
I'm the face of sarcasm. I'm here.
And you're a face.
Yes. Allegedly.
That's quite true, then. Yeah. So today's episode, we're going to talk about the International Sun-Earth Explorer 3, the 3th one.
The 3th.
And as a warning to all of you listening, I made these slides several weeks ago, so I don't exactly remember everything that was on them. This should be fun. So Earth has a magnetic field, and that was created by dropping nuclear bombs into the center of it.
Ah,
You saw the
yeah.
documentary film, Car? Yeah. So the ISEE program is a joint effort between NASA and ESRO, now ESA, to study the interactions of solar wind and Earth's magnetic field. Right? Solar wind comes and the magnetic field's there.
Yeah, and it's
It does
deflected
things.
and bends it and does some...
Yeah,
Yeah.
as you can see by this diagram here.
Yeah. The sun's over there. You don't have to draw it again. And then you have the Earth over there on the left. And...
See it smiling.
right. Okay.
Yep. So this is actually part of a long duration program called the Interplanetary Monitoring Program, IMP, which interestingly are the first spacecraft to have used integrated circuits.
Really?
Yeah.
Huh.
IMP.
So before they were just doing vacuum tubes?
Vacuum tubes, memory rope, most likely memory rope, you know, hard coded. So there's little rodents in there doing the science.
Just chiseling everything into stone tablets.
Yeah, how do we get this back? I don't know. So ISEE 1 and 2 are sister spacecraft with 4 goals.
Okay.
Investigate solar terrestrial relationships at the edge of Earth's magnetosphere.
Ooh.
2. Yes. Examine the structure of solar wind near Earth and the shock between the magnetosphere and solar wind. So you can actually measure where Earth's magnetosphere ends and interplanetary space begins.
Oh, wow, okay.
Yeah, and some of the results we'll look at, you actually see it.
Nice.
3. Investigate motions and mechanisms of plasma sheets.
What's a plasma sheet?
So, well, it's when you go to bed, right? It goes under your blanket to, you know.
Ah, okay. So instead of having like a solid blanket, you instead have a plasma blanket.
Yeah, it's from Star Trek.
Got it.
Yeah. 4. Continue investigations of cosmic rays and solar flares in the interplanetary region at 1 AU, where the Earth is.
Right.
So ISEE 1 and 2 launch on October 22nd, 1977. Wait, is that a diagram? No. Sorry, I've been using this thing where you do the slides where it's like multiple pictures with the same text, so I don't remember how much I did.
Oh, okay.
Oops. Yeah. So they launched in October 1977 to a very large orbit. So it's 85,000 miles by 4,100 miles.
Oh, wow.
So that's 100. Yeah.
So that's really elliptical.
It's a really elliptical orbit. Yeah, so the orbit is actually 2 days, 11 hours, and 16 minutes long.
That's quite a long time to be in orbit.
That's a really big orbit.
Yeah.
But ISEE-3, now that one's going to Earth, Sun, L1.
Ooh, the Lagrange point.
So, as a recap, since we discussed this about a year ago now, if you do n-body physics with the Sun, which is here, as you can see, I drew it differently. So we have gravitational fields, as you can see by these different lines here, that that show kind of where gravity's pulling you, right? And you notice there's 5 places where gravity kind of balances out between the Earth and the Sun if you're a spacecraft, right? L1, L2, L3, L4, and L5.
Okay.
Now, up here at L1 and L2, you can actually orbit these.
Oh yeah, isn't the James Webb Space Telescope orbiting L2?
Yep. So James Webb is right there,
Okay.
orbiting that. It's a spot there, kind of like a seesaw. We talked about this Titan Hagoromo a little bit. And so they want to put it up there because, interestingly enough, L1 is about the edge of Earth's magnetic field.
Really? That's convenient.
Yeah, how convenient. So they'll put a spacecraft up there to do the same monitoring of solar winds and plasmas and all that, because it's right there. And it's also up close with the sun, and it's kind of easy to get to. And this guy on the right is Bob Farquhar. He's the guy who designs the trajectory for this.
Okay.
Because he came up with something called a halo orbit versus, a Call of Duty orbit.
Mm-hmm.
So halo orbits are orbits around L1, L2, and L3 in a three-body system where a spacecraft could orbit the point with some minor thruster corrections.
Okay.
Bob described these in 1966 for his doctoral dissertation. And he actually proposed one for a data relay satellite around L2 for moon missions, because the original plan for Apollo 17 was to land on the far side of the moon.
Oh, and then you need a communication because you can't do line of sight. So you need so you put up a data relay satellite up at orbiting L2 in a halo period, in a halo orbit.
Yeah, because it can see the far side, but also the way that the orbit works, because you're orbiting the point, you actually get to see Earth too, and it acts as a relay. And actually, the Chinese do have one of these right now.
Oh, really? That's awesome.
Yeah, because the Chang'e 6 did the far side sample return, so I had to talk to it.
Ah. And so the L2 is rotating, or is orbiting with the moon then, right?
Yep, it's a spot, because L1 is here, you have L4, L5, and they move with the moon.
Got it.
Because where the moon's Earth's gravity kind of balances out weirdly.
Yeah. Lagrange points are weird.
Oh, yeah, in n-body physics. Uh-oh. But so the reason they didn't do the Apollo 17 landing on the far side is it would cost $60 million to build the relay, and I guess they just said, nah, we're not going to do that.
Yeah.
So Bob himself was born on September 12th, 1932, and he died in October 2015. So his work, he did a lot of good work with orbital mechanics and mission design. He worked on Near Shoemaker, which landed on an asteroid.
Ooh.
Contour, which famously exploded. Mm-hmm. Messenger, because that one had to do a lot of orbital mechanics to get around to orbit Mercury.
Right.
And then did some of the early trajectory design on New Horizons.
Ah, yeah. Okay.
Yeah.
So an orbits guy.
Yeah.
Wizard of orbital mechanics, yeah.
So this is ISEE-3. They didn't get a number until they actually worked.
Oh.
So Soviets did a similar thing where, this is Cosmos number, and if it doesn't work, it doesn't exist.
Well, that's easy.
Yeah. So it's also known as Explorer 59 because it's also part of the Explorers program. We're still launching Explorers technically, which is weird.
That's weird.
So this thing weighs about 1,000 pounds, about 479 kilograms. It's got about 196, so about as much my weight in propellant on board. It's about 89 kilograms.
Oh, of the hydrogen. Okay, yeah. Okay.
Yeah. It's toxic like me.
Of course.
Because hydrogen's toxic. I'll shut up now.
Thank you.
So it's about 5'10", or 1.77 meters tall, so my height. This thing's just me, I guess.
Yeah.
And it's about 1.58 meters across, so 5 feet, 2.5 inches. Also like me. So you can see it. I think it's a 16-sided spacecraft. I think it says.
Yep.
Yeah. And it's going to rotate at 19.76 revolutions per minute, and it's got 13 experiments on board. So just want to take a look at this just take a look at it from here. So it's got it's got a lot of antennas. There's no cameras on this one, by the way, so there's going to be no pictures.
Cool.
This is going to be wonderful. Okay, so wait, let me just check something. Okay, no.
Correct, no pictures. You're just double checking that.
Just double checking. Any pictures in this? No. All right, so experiment number 1, X-rays and electrons. It's going to observe X-rays from 8 to 72 kiloelectron volts and electrons from 2 to 1,000 kiloelectron volts. If you're one of those people who likes these kinds of experiments, I'm assuming this is very enthralling.
Probably.
Experiment 2, solar wind plasma. This one observes ions from 0.15 to 7 kiloelectron volts, electrons from 0.05 to 2.5 kiloelectron volts, and it will be used to form a 3D distribution of kind of what, because you got all these antennas pointing out, right? So you can make a 3D model of what's coming in.
Okay. So they're just mapping out the whole thing of where the plasma, the solar wind plasma is.
Yep.
And they're just doing this manually.
Yeah. So 3, high energy cosmic rays. Observes ray species of hydrogen to iron with a resolution of 0.15 atomic mass units. So there's cosmic rays coming in. They're little atomic nuclei. So that's what it's looking at.
Okay. It's just all the atomic nuclei smacking in. Okay.
Yeah. Low energy cosmic rays. So these are the ones coming in while they're asleep. This observes particle composition up to 20 mega electron volts per nucleon.
Okay.
Very exciting. This is enthralling. I'm very sorry.
Yeah. So if you don't know anything about electron volts, this is.
Oh yeah, this is exciting.
You're
This
normal
mission is
like me.
Yeah, this mission is exciting for not the science package. For no other reasons. It's not that. I'm sorry. Unless you really like these kinds of experiments, I'm boring you to death. I'm sorry. And if you do like these, I'm sorry for making fun of the thing you like. Okay? You in your basement write some angry letters. Okay, so energetic protons. So these are the ones that are all up and atom. These observes protons from 30 kiloelectron volts to 1.4 mega electron volts and particles from 1.4 to 6 mega electron volts.
Okay.
I know, it's gripping.
Yeah, I understand exactly what they're doing.
Again, it's pretty much the energies of these protons. It's going to figure out where those are, how many of them are hitting the spacecraft.
Okay,
Right.
basically just figuring out what it looks like in terms of electron volts. Okay.
Yeah, and electron volts are just kind of the energy and also kind of the temperature. Because you get down to the nuclear side of things, it's really weird.
Quantum physics takes over and all common sense just gets chucked out the window.
Yeah, orbital mechanics all the way.
Ooh.
So 6, cosmic ray electrons and nuclei. Wow.
I wonder what this is
Particles.
about.
So it's looking at electrons and protons to certain mega electron volts, and it's looking for elements of helium to sulfur from 60 to 13,000 mega electron volts per nucleus, and the iron group from 150 to 13,000 mega electron volts per nucleus.
So why are they looking at the helium, sulfur, and iron groups?
Because that's what the solar wind is made of.
Oh, really?
Because it's particles coming out of the sun, and the sun is making all of them through fusion.
Oh, yeah.
Right?
Yeah.
So that's what's coming out of it. That's what they're looking at. It's like, hey, what's the sun giving off? You know,
Okay.
good vibes, bad vibes, sulfur vibes. Who knows?
Iron vibes.
Speaking of sulfur, I forgot to tell you this.
Yeah.
Was it Perseverance? Yeah, or Curiosity. The new rover rolled over a rock and then looked at it and found pure sulfur crystals.
Oh,
this
wow.
week.
Oh.
They're not supposed to be there. They don't know why.
How'd they get there?
That's a good question. Science. That's really. I'll show you pictures of this after this.
Okay.
It's really interesting. So 7 is plasma composition. Okay, wow. So it's 470 electron volts per magnetic field to 1.5 kiloelectron volts per magnetic field. I think that's what the Z is.
The Z. I'm assuming that's direction,
Or
right?
it's-
Because you can see in the diagram there's the X, Y, and Z directions. So.
Or it's atomic mass units. I don't know. And it's looking. It's the ratio of something to 1. I've linked all the papers about these experiments in the description. If you really like these kinds of experiments, you can read about them. I'm sorry. So looking at plasma waves, the magnetic field and electric field, so, right, because it's electromagnetism.
Same thing.
It's 8 channels, 60 decibels in size, 20 hertz to 1 kilohertz, and the electric field is 16 channels, 80 decibels to 20 hertz to 100 kilohertz. Right, it's looking at these at different channels.
Yeah, 24 channels, nothing to watch.
Yeah. So you can see, of course, here's all where the experiments are mounted on the spacecraft.
Basically,
Also,
out.
one of these, the 3D radio mapping antenna is actually like 300 feet wide.
Yeah, you can see radial
It's-
92 meters.
Yeah, it's enormous.
Yeah. This thing's wide.
So, experiment 9, radio mapping. So it's 3D tracing of paths of type 3 bursts. That's something from Star Trek. Okay,
Yes,
this is just Star Trek. The 20 kilohertz to 3 megahertz band.
Oh, yes, data. That sounds good. We'll reconfigure the deflector dish.
Make it so. 10, helium vector magnetometer. That actually sounds pretty cool.
Yeah.
So it's doing 8 ranges of the magnetic field. It's Gauss. That's what magnetic field strength is.
Okay.
So it's 4, 14, 42, 640, 4,000, 22,000, and 140,000 times 10 to the negative fifth Gauss. Frequency response from 0 to 3 hertz with 3 bands, 0.1, 1, 1 to 3, 3 to 10 hertz, for measurements of fluctuations parallel to the spacecraft spin axis. So
Okay.
helium's going to hit it, and it's going to have a magnetic field, and it's going to see what it does.
Cool.
Very exciting.
Mm-hmm. Enthralling.
If I understood any of this, I would be way more thrilled. 11, high energy cosmic rays. So it's going to do the charge, isotope, and energy of lithium to nickel and lithium to nickel isotopes are going to hit it. It's going to figure out what the energy and the charge of those isotopes are going to be.
Okay.
Right. Again, it's going to be hit by particles, cosmic rays, and it's going to figure out what they are.
Cool.
Medium energy cosmic rays, nuclei. I'm just going to skip ahead now.
Yeah.
Nuclei,
There's a bunch of
isotopes.
letters and numbers on screen. You can look at those and make what you will of them.
Look at all these mega electron volts per nucleus. Wow, that's exciting.
Yeah.
So 13 is ground-based solar studies. So it's going to assist with, again, it's going to talk to ISEEs 1 and 2, which were launched actually in parallel on top of each other.
Oh, they were just stacked.
Yeah, they're just stacked on top. Because ISEE-1 was built by the U.S., ISEE-2 was built by the Europeans. It's to help build 3D models of the magnetic field.
That makes sense because you have two reference points then.
Yeah. So of course this is more of the spacecraft, as you can see.
Yeah, all the antennas just sticking out the side that are
All those
giant.
all these really exciting science experiments that I don't understand.
I mean, hey, if you're into electromagnetism, this is fantastic. If you're
Yes.
not, like normal people, then
Yep. So this is no more pictures of it. So actually one of these experiments, I think it's the gamma ray burst detector, is also on Voyager 1 and 2.
Really?
Yeah, one of the experiments on this is the same as on Voyager.
Wow. Because it
think
makes
it's the
sense
gamma
because it launched 1977, right?
Yeah, it's both around the same time.
Yeah.
So that's the spacecraft there, and here it is under construction, as you can see. So you can see about the size of it.
Yeah, it's decently sized.
It's a decent-sized spacecraft. So here's Bob, his wife, and daughter in front of it. So you can see there's the experiment package. And so right here, these are the thruster pods.
Ooh.
This will be important at some point. And there's the big antenna and all that fun stuff. It's really exciting. This is a really interesting mission. Don't worry.
Very.
So here's a picture of the launch. And this is where it's going to go. So it's launching from Earth August 12th, 1978. So that's your minus somethingth birthday.
Thank you for doxing me.
Again. This is the second time we've had an August 12th. So it's going on a long way up to L1, and then it's going to start orbiting it.
So this is to scale, right?
I think so, yes.
That is a large orbit.
Yeah, the orbit is a 6-month-long orbit.
Wow.
Yeah. So it launches August 12th, 1978. It's launching on a Delta 2914. As you saw it there, the little Castor 2s on it. It's a cute little guy. So it enters service on November 20th, 1978 at nearly 1 million miles out in the Halo orbit. It's about 1.5 million kilometers. So it's going to orbit L1 about 4 times between November 1978 to June 1982. And that's the length of the mission plan.
Okay.
Right, so you can see, of course, here's the orbit, here's where it is, and the sun, of course, is over here. I'm going to draw it.
Differently
There's
every
the
time.
sun. Differently, yep. There's the sun, it's all happy.
Mm-hmm.
So we're going to talk about some science results from this, because I think it's easier to do it this way. So here is particles, solar wind hitting it on July 6th to July 7th. So you can see, so what this is, these are the velocities of helium and hydrogen isotopes being thrown off the sun.
Okay.
right? So you can see these.
So I was
and
looking
there's
at the
shock.
speed of it.
Yeah. Oh, yeah, those are going really fast.
Yeah, so that's... Yeah, that's 500 kilometers per second.
That's going off.
Yeah, that's going on. Dang. And then it just jumps up to over 650 kilometers per second.
Yeah, so that's kind of so the magnetic field. Again, it's our shield, right? As the documentary film The Core discussed.
Mm-hmm.
So yeah, you can see. So that's again. If you really like solar wind, this is a way more interesting mission.
Yeah.
And I'm just breezing through it. So the other thing here is these are the temperatures of the different ions that hit the spacecraft.
Okay.
You got helium, oxygen, and iron.
Okay.
Yep. So you can see the temperature varies over time.
Yeah.
That's exciting.
Uh-huh.
So these are different channels for the electromagnetic field I was telling you about, right? It's got 16 channels, nothing to watch.
Mm-hmm.
So it also detects something called whistlers in the solar wind. I don't know what those are, but they sound interesting.
Yeah.
So you can see here, and here, right?
Yeah, it's spikes.
Yeah. That's pretty interesting. So I guess and there's our type 3 radio bursts in the diagram there.
Okay.
So I wonder I think it must be just different particles interacting with magnetic field doing things.
Yeah. Something like that. I don't know.
Yeah, again, if you like electromagnetism, you'll love this part, and you're mad at us right now.
Right. Okay, so we discovered that the sun whistles through the wind. Huh?
Yeah. Oh, maybe it thinks ISEE-3 is very attractive.
Ooh, trying to catcall it?
Yeah.
Don't do that now.
You can't do that yet. Well, that's before everything went woke.
Yeah, of course.
Yeah. So here's more data on halo electrons. So up there, so you can see the speeds of them, components going away towards. These are protons hitting it.
Somebody playing Tetris.
Did I tell you my new high score, by the way, in Tetris?
What's your new high score?
338,000.
Nice. Okay.
Yeah, it's a really good high score. So here's some energetic protons. They took their coffee this morning. They're not playing Tetris.
Mm-hmm.
So you can see, them coming in. Protons, again, very interesting, isn't it?
Yeah. Why is it pointing to a bubble line?
The bubble might be a plasma bubble in the magnetic field, right? Because there's the shock of it.
Mm-hmm.
So it might be something that encountered on the way up.
Okay.
Yeah. Because they have little plasma bubbles that form in the magnetic field, I guess, because of all this going in.
Mm-hmm.
It's really interesting, but I don't understand it.
Yeah. You don't say.
Yeah. So that's what's coming in. Okay, so since 1981, now what do you do with ISEE-3? Right? Primary mission's pretty much over.
Mm-hmm.
What do you do with it?
Something interesting? I don't know.
it's still working. So option 1, this is the exciting one. Keep doing what you're doing. It's a space weather platform. Isn't that exciting?
That is really exciting. It's very exciting.
Option 2, nudge ISEE-3 to Earth's Geotail. So go to L2.
Okay. Option
3, somehow use the spacecraft to perform a flyby of Halley's Comet in 1986 and eventually return to Earth.
Okay, that sounds exciting. We should do that one.
That's way more exciting.
Yeah.
Okay, check. Yep. Okay. So this idea is posited in early 1981 by a man named Fred Scharf. At the time, NASA was considering a spacecraft mission to Halley's Comet since the Japanese, the ESA, Soviet Union were also planning their own missions, right?
Mm-hmm.
There's Giotto. Someone told me I pronounced it wrong the last time. So that's Giotto under construction. Of course, our good buddy Vega, which you last saw.
Yeah.
And of course, the Japanese. So the only American missions that are kind of looking at Halley's Comet at the time, this is Pioneer Venus Orbiter. So it's orbiting Venus.
Mm-hmm.
So we'll take a look at Halley's Comet. We also have some of the Pioneers that are also part of the space weather monitoring platforms, but no dedicated missions.
Okay.
Right?
Yeah.
By late 1981, NASA abandoned plans to build a spacecraft to go to Comet Halley because it cost about $200 million.
Yeah, it's a bit pricey.
Using ISEE-3 would be about $5 million, despite the fact it's not built to do this.
But hey, maybe you can monitor, the electrons coming off of it or something.
Yeah, it's got plasma and stuff coming off. I saw Star Trek. It's got plasma.
Yeah, everything's got plasma.
Yeah. So NASA funds and approves an extended mission for ISEE-3. Now, did I mention this? Okay, so NASA's real plans were to observe Halley's Comet from the shuttle in early 1986 on STS-51L and then STS-61B, I think. Now, of course, 51L failed and exploded.
Yeah.
That's Challenger. So that didn't happen.
Yeah.
So, a bit fortuitous on our part to do ISEE-3. So, in 1982, spacecraft leaves L1 for the Geotail. So, as it's setting itself up to fly by Halley's Comet, it's going to go flybys of the Geotail. Because why not? You're there. Why not do this?
Right. Okay.
So, it's gearing itself up for a December 1983 departure to first Jacobini Zinner in September 1985, and then Comet Halley in 1986.
Okay.
So, this is the interesting part. So, right, it departs. Look at that little delta V, 4.5 meters a second.
Oh, that's barely anything.
Right, so it's going to fall back in. It's going to fly by the moon. It's going to go up. It's going to go in, fly by, go up. There's L2, right? There's the Geotail, as you can see in the diagram. It's going to go back, fly by the moon, and then it's going to go back, right? A lot of maneuvering going around, right?
Yeah, we go out to this faraway place, and then we come back. And then we go out to this other place, and then we come back.
And we come back. Yep. And then, so here's another one. Oh, I forgot to draw the sun. Uh-oh. Oh, no. There.
You don't have
the
to.
Sun. I'm drawing it differently, though.
Why?
That's the sun. Right, also, I heard stories that Bob was so good at orbital mechanics that he timed these flybys to people's birthdays and anniversaries.
What?
Yeah. He made this so the flybys would happen on, mission team members' birthdays.
Oh, that's nice.
It's cute. Yeah. That's nice of him. Show off.
Yeah. Look how good I am. I can line this up with your birthday.
Yeah, look at me. Aren't I cool? I sit here podcasting. Right, so it's going to cut, right? So they'll do a fly by the moon, go back up, come back in, fly by the moon, and get tossed out.
Okay.
So here's some results from the Geotail.
Ooh.
So it's working in conjunction with ISEE-1, right? As you can see. So there's plasma. There's plasmoids that are being made in interactions with the magnetic field and solar wind, right? Because they're charged. There's charged particles coming off. There's a magnetic field that's making what are called plasmoids, and it actually observes these, right? So it makes a tail of them, and then it makes a little blob that falls off.
Oh.
Right.
Wow. Okay.
It's really interesting. And so what it's doing is you have ISEE-1 monitoring it, then you have ISEE-3 getting up close to them, right? You can see in this diagram. And it's actually taking magnetic field readings of these plasmoids that are forming. And remember, you can't see them. They're not they're not like in Star Trek, where you can see this big glowing ball of something.
Yeah.
Which really saves on the VFX budget. So that's what it's doing as it's going through. It's one of the things it sees.
Wow.
So here's some magnetic field stuff as it goes in and out, right? Magnetic field data goes day, so it's going. Here's magnetic field. Look, wow, exciting, isn't it?
Yeah, look at this squiggly line.
Yeah, look at that. As you can see, it's doing some stuff. There's also lobes to Earth's magnetic field, apparently.
Okay.
Yeah, I was looking through all of these, going, how do I parse any of this?
Well, I mean, if you go back to the one previously showing off the different plasmoids, right? I like that you can kind of see going from the top diagram down and then to the next one over. You can kind of see it the one forms and then it goes off and then it turns into a stream and yeah.
Yeah, it's kind of like a droplet, right? Like a water droplet.
Yeah. That's cool. That's interesting.
That is very interesting. Yeah, so it does a lot of mapping of Earth's magnetic field. It really helps with that.
And it's really dynamic, apparently.
Oh, yeah, Earth's magnetic field is very dynamic. It's very interesting. It's just, I don't know how to parse any of this because I'm not a electrical fields guy.
I would say you're normal, but that's incorrect. So
I run a podcast about space missions with details. Not the cool fun stuff. It's look magnetic field data.
Behold the Fourier transform.
Yeah, Fourier transforms. Those are pretty cool, actually. Yeah. So this is all that's going on there. It says G sex. It's G and then spacecraft Earth X, but
right.
That's actually where it is in radii. But yeah, this is what the data it's getting, and just again, the description has a lot of diagrams that explain more of what's going on and kind of the data that's being gotten from the spacecraft. So, this is what Earth's Geotail is like. So in total, they only use 77.25 meters a second of propellant.
Wow.
So it's about 254 feet per second.
That is just tiny.
Well, you remember, if you think about it, right? ISEE-3 is basically outside Earth's sphere of influence. It has all the energy to just escape. Right?
Yeah.
So all you have to do is squirt and you fall right back in or you fall right back out. You have all that energy and you just go around anywhere in the solar system, or the Earth-Moon system.
Yeah. Dang.
So you can do this in Kerbal Space Program too. Not to the same extent, of course, halo orbits, but you can still see once you get to a certain altitude, you can kind of go anywhere with not much. It's just getting up there that's the problem.
Yeah. That's where it needed the big rocket for.
Yeah. So on December 22nd, 1983, ISEE-3 does a lunar flyby, the final one, to get tossed out to the Comet flyby in 1985. And it only goes over the surface by 120 kilometers, about 75 miles.
Oh, dang. That's close.
It's really close. Now, in September 1981, the onboard battery had failed. So there were some concerns because it's going into the shadow for 28 minutes.
Ooh.
Right? So the spacecraft was not in communication with the ground for about an hour. That makes sense because it's it's in the dark side, the side you can't see. And
if only we had some communication or data relay up at the Halo L2.
If someone had done this, if only someone could have done this or thought of it by now. I don't know.
Dang. Oh well.
I guess we're just so as it flies out, it's now renamed International Cometary Explorer.
Ooh.
Because it's it's no longer doing Sun Earth stuff because that's nerd stuff. We're going to a comet now, okay?
Yeah.
Comets are cool.
Yeah.
So
this weird electromagnetic plasma stuff. Who cares? Let's just look at a comet.
Yeah, comets are cool.
Yeah.
So the arrival is set for September 11th, 1985, but the error for the of hitting it is about 1 day. It's going to be off by a day getting there. But they're going to do a trajectory correction in 1985. And actually, one of the concerns with talking to ISEE-3 is that it was only built for going out 1.5 million kilometers. It's how do you talk to it when it's not designed to go really far away from the Earth?
Well, in Kerbal Space Program, you quickly whip up another communications relay and then just launch it as fast as you can. That's what they do here, right?
Or you go into the game settings and you change it, so you have a constant data. Yeah. So the original plan was just to bounce signals off the Japanese spacecraft, because the Japanese spacecraft could talk to Earth, because it was designed to do that. But then it turns out the Deep Space Network was actually good enough to actually listen to ISEE-3. It's just, so the data transmission rate started off at like 2,000 bits per second, but for the Comet flybys, it's down to like 120 something.
Wow, 120 bits per second.
Yeah.
So it'd take you like, what, a minute to get a Word document or something? Is that correct?
Probably.
Yeah.
Probably. I'm not a computer person.
Yeah.
So on board is about 223 meters per second of delta V, just as a quick note.
So it's only used like half of it.
Yeah. Because it's got to do some trajectory corrections to get up to Halo orbit, put itself into Halo orbit, and now it's going back out.
Okay.
So here's a painting of it doing a flyby of the moon. Here's our spacecraft, right? All the antennas and all the plasma wave experiments and all that fun stuff.
Mm-hmm.
All the science things that I don't understand.
Mm-hmm.
So here's Comet Giacobini. I'm probably pronouncing it wrong. Zinner's orbit as it's coming in. Big inclination. And it's actually, this thing's going to get, it's only going to hit it like on the perihelion, too, for the comet.
Oh. So,
Yeah.
like, right at the closest point.
Yeah. So that's, you're going to get some really good data from this.
Yeah.
So let's talk about, here's the comet. Here's a picture of it. So it's
Wow.
21P. It was discovered in 1900 and 1913 by two different people, Michel Giacobini and Ernst Zinner. That sounds like discount versions of Michael Giacchino and Hans Zimmer, the movie composers.
Yeah.
That's what it sounds like to me.
That's kind of funny.
That is really funny. So the size of the comet, it's about 2 kilometers across. It's about a mile and a quarter. So you could run that. I could run that.
Yeah,
If I didn't have a
you
shin
run
splint.
that. Yeah.
If I didn't have a shin splint.
You can do it with a shin splint. It's not that long.
No, I'll make it worse. That's the problem.
Yeah.
I go to the gym and I walk 3 miles now instead of run. It takes me 45 minutes. It's annoying. So the orbit is 1.009 by 5.97 AU. So it's 1 by 6 AU.
Okay.
So it's so the orbit's about 6.5 years. The next perihelion is next March.
Oh, nice.
So so we could do something. Let's build a spacecraft and launch it.
Yeah.
That should be fairly easy.
Yeah. I mean, it's notoriously inexpensive to launch things into space.
Yeah, I can do it.
Yeah.
I know a guy. So actually, this comet is the source of the October Draconids meteor shower.
Ooh.
Yeah. That's all that's interesting about this comet, except for the fact that ISEE-3 flies by it.
Well, I mean, it's fuzzy. It looks kind of green.
Yeah. That
Yeah.
might be oxygen, I think. Yeah, it's oxygen.
Cool.
Or water or something.
And it's
Yeah.
named after discount composers, so it's
Yeah.
phenomenal.
So actually, the Japanese Halley's Comet visitor, Sakigake, was supposed to do a flyby of it, but it ran out of propellant. So we're not going to do that.
Oops.
So before its arrival, Pioneer Venus, the one orbiting Venus, did some observations to kind of, prep ISEE-3, right? Because the last thing you want to do is get data and go, wow, this is so exciting, and then it's actually wrong.
Oh, yeah.
Right, so using this to kind of do that check. So this is the flyby on September 11th, 1985. It flies by at 7,800 kilometers, about 4,800 miles away.
Mm-hmm.
So you can see it goes straight through it.
Nice.
And that's the comet. There's a solar wind, right? It's got the bow shock, you got the dust.
Dust.
Don't worry.
Yes.
Don't worry.
Oh, we
This
got.
is
Oh,
actually
good.
Yes. So you also have magnetic fields, of course. They're draped, though. So you got the,
Yes, of course. The lovely drapes.
Of course. Right, so the comet does a flyby, right? So it's got plasmas, it's got, right, electromagnetic stuff, the stuff that this thing can look at.
The boring nerd stuff that it's designed for.
Yeah, the Star Trek stuff. This is the first ever comet flyby.
Really?
Yes. For a spacecraft that was not designed to do that, just to beat everybody else.
Wow.
Isn't that great?
Yeah.
It's hilarious. So, the thing we've all been waiting for, the most important part of any science mission.
The
Dust
dust
counting.
count. Yes.
Because our particle detectors can detect dust. Because dust hits it, makes a little magnetic field, an electromagnetic field, and you can detect that. So those are dust impacts. You can
Yes.
detect dust. So you can see, as it flies through, there's dust.
There's dust.
Look at all that dust.
So much dust. Oh my gosh.
Look at all that dust we can hit. Oh, yeah. Most important part of any science mission.
This was worth it. This was worth it.
Absolutely worth it right there. So it also does electron densities, right? So it's counting electrons as it goes in and then it goes out. So you can see there's more electrons as it gets closer,
Mm-hmm.
and less electrons as it goes away. Almost like there's a tail or something.
That's weird. That's weird.
I know. On a comet?
No, they don't have tails.
No, not at all.
No.
So yeah, so that's just any more. Oh yeah, so it also gets like the noise. This is the plasma diagnosis. Again, Star Trek stuff. So this is kind of, yeah. What's interesting here though is like there's thermal noise, like galactic noise it's picking up. So,
Oh, wow.
so the frequencies that the frequencies it's picking up here are that's thermal. So that must be so it's thermal. That means like something's hot because it's giving off because hot things give off stuff.
Heat, yeah.
I think his dad's told us about this because he's an electrical engineer with radio frequency stuff, and he does talk about the temperature of things influencing like signal propagation and things like that.
Yeah.
Right. So that's galactic noise. This is the galaxy, so it can actually hear the galaxy.
Yeah, turn
which makes
into
sense.
Yeah. Because it's
So
blasting
we got-
out some awesome tunes and beats.
Yeah. In the 70s, though, so it might be disco.
Yeah, never mind.
Well, this is 1985. Disco's dead.
What was happening in the 80s?
Hair band? A lot of hair bands.
Yeah.
That's what's listened to.
Maybe don't listen to it.
I don't know. So here's, of course, the density of the particles, the temperatures of the particles, as you can see.
Mm-hmm.
Again, basic plasma stuff. And then here's the ion composition chart. So how fast they are, and then the weight of them.
Okay.
Yeah. I thought that was pretty neat.
So the heavier they are, the slower they are.
Weird.
That's a
is
bizarre
momentum
relationship.
I know, right?
Yeah.
So then we have so these are compositions of different things as it detects them, actually, right? So you have water ions, you have hydroxyl groups, got carbon. I don't know what that is. Non-commissioned officers,
Commanding
carbon dioxide,
officers.
right?
Yeah.
Yeah. So just these different ions are being particles are coming off the comet, of course, because it's got the different compositions being flung off,
Mhm.
and this is of course counting the space. Actually counts per spin because it's still spinning, of course.
Right.
Yeah. Isn't that cool?
Yeah.
It's neat. Again, first spacecraft to fly by a comet, not designed to do that.
Nice.
So then it goes to Halley's Comet.
Yeah.
Now we've been there already with Vega 1 and 2.
Mhm.
So this thing's about 11 kilometers, about 6.8 miles across. Its orbit's about 0.6 to 17 AU, so it's got a 74.7 year orbit.
It's once in a lifetime.
Obviously, it's once in a or twice, depending on when you're born, like Mark Twain.
Mm-hmm.
We talked about it with the Halley Armada, Vega. So the encounter with Halley's Comet's on March 28th, and it does a 28 million kilometer or 17.5 million mile flyby.
Is that even a flyby at that point?
It's in its vicinity. It can see it. There it is. But it does do some particle detection.
Oh, good.
So it encounters the tail of Halley's Comet 1 to 2 weeks after the main Halley Armada. Data is mostly used to help build models of comet tails and to correlate with the much closer Armada data. So this is dust data from it. I couldn't
Yes.
find that many papers on the data from the Halley's Comet encounter. I might have been looking in the wrong places, but so this is a modeling based off of what ISEE-3 got, and like there's Geotail, of course, all the particles it detected, and of course the Helios spacecraft were launched in the early 70s on Titan 3Cs. It's the fastest spacecraft ever built until Parker Solar Probe, so it's correlating those.
Ah, okay.
And so I guess it's looking at solar data as well. That should make sense because it's you to fly by your back and around the sun.
Yeah.
So now what?
You gonna bring it back to Earth?
So what's next? So option 1, return to L1, act like nothing happened, because moving the spacecraft away from there actually annoyed a lot of scientists.
Really?
Yeah, they called Bob a space pirate for stealing their spacecraft.
Bloody
so
pirates.
Option 2, return. Yar. We stole the spacecraft to look at comets and count dust. Yar.
You can't stop us.
Yar. Option 2, return to Earth, use aerobraking maneuvers, and then get to low Earth orbit and have the shuttle recover it.
Ooh, that's an option.
That's a good idea. On September 11th, 1986, the Air and Space Museum actually got ownership of the spacecraft.
Oh, wow.
Technically, they own it. Because if they brought it back with the shuttle, it'd be put on display. Yeah. So what actually happened? More heliospheric science. It's still up there, why not? So it's part of the Space Weather Fleet and ends up mostly performing observations and data processing in coordination with the Ulysses spacecraft. That's this guy.
Okay.
Ulysses.
Okay.
Yeah, so Ulysses actually went to Jupiter like a week before Galileo to do a flyby to go into a polar orbit around the sun.
Oh, wow.
So this is talking
oh,
to,
yeah.
So they're talking to each other. Don't worry, we'll cover that one. Ulysses is a very interesting mission, but that's it. But here's the thing. It's May 1977. End of mission.
That says 1997.
It's not... Yeah, that's what I said, right?
You said 77.
Look, all the plasma diagnostics got to my head, okay? I've been, I was counting some galactic nuclei, and I'll do better next time, okay?
I accidentally started listening to the disco music, and I thought we were back in the 70s.
Yeah, just all coming back to me, man. Look, it's not non-flashbacks, it's disco flashbacks, man. Oh, the glowing ball. The mirror sphere, man. It's all coming back. Oh, God, I'm putting the bell bottoms back on. Oh, no.
Gonna go roller skating.
Let's go to the roller disco, man. It'll be groovy. So, on May 5th, 1970... God dang it.
It's the disco.
May 5th... It's the disco, man. It's the ball that hypnotizes you. And a bit of the jazz tobacco. So on May 5th, 1997, okay, NASA declares end of mission for ISEE-3, but it leaves the carrier signal on for a little bit longer to do ranging, right? Because it's out there, you want to just test out the deep space network, just, okay, let's make sure this all still works, because you can use the radio signal to kind of find out, where something is.
Right.
So the orbit it's left in is 0.93 by 1.03 AU, right? Basically an Earth orbit. Period of 355 days and an inclination of 0.1 degrees. Right. And that's ISEE-3. Or is it? So here's the thing. It's called orbital mechanics, right? ISEE-3's orbit means it comes close to Earth every once in a while. And if you look at this date right here, what does that say?
Return 2014. You crossed it out a little bit. Is that August 10th, 2014?
Yes. The way the orbit was designed is that it would come back to Earth in 2014 on its own.
Oh my.
So here's the thing. So in 1999, JPL uses the Deep Space Network to verify the carrier signal of ISEE-3. And at that point, they're supposed to tell it, all right, good night, go to sleep, whatever. But here's the thing. In 2008, Kinetics, they're using the Deep Space Network, discovers that ISEE-3 wasn't actually turned off.
They forgot to hit the power button?
Yeah. Last guy left forgot to turn off the lights. And that 12 of the scientific experiments are still operational. And it has about 150 meters a second of propellant left.
So it's still workable.
It's still there. It's still kicking, right? So NASA actually begins studies on recovering the spacecraft in 2014. So here's the trajectory as it's going to come back in, right? So it's coming in like this. So its perigee will be on August 9th, but it's going to do a flyby of the moon on August 10th.
Okay.
Right? So what do they do? So it's still alive. It still works. What can you do with it? So one idea is just bring it back into the system, right? Use the lunar swing by, put it into highly eccentric Earth orbit, and then toss it back out. One option was Giacobini Zinner to do a flyby in 2018. So go back. Contour was supposed to do that, but of course it exploded, famously. Yeah. Or toss it back to L1 because you're supposed to put it back, you pirate.
Return the spacecraft.
Yeah. Pirates of the Caribbean.
It's like the Return the Slab.
Oh, yeah, Return the Slab. Or it's like Pirates of the Caribbean, right, with the gold. Right, they're going to go back.
Oh, return all the Aztec gold.
You got to put the dust
Bloody
back,
pirates.
Exactly. But interest in the plan wanes. ISEE-3 is an old spacecraft. Again, it was made in the disco era. And the encoding equipment for it had already been scrapped. But that doesn't mean NASA is the only person who can look at it. So in early 2014, the ISEE-3 reboot project is started.
Ooh.
And it's started by this team of pixels over here.
You're standing outside of a Pizza Hut?
That's a McDonald's, actually. So
Dang it.
It's an abandoned McDonald's at Ames Research Facility in San Jose, California. And actually, if you look over here, that's a Titan 1 first stage just left out there. Someone's trying to restore it.
That's funny. I was kind of distracted by the Jolly Roger they have hanging in the window.
Oh, yeah.
The center window.
Yeah. So the ISEE-3 reboot project is started by two guys, Keith Cowing of NASA Watch and Dennis Wingo of SkyCorp Inc. Wingo has previous experience in the Lunar Orbiter Image Recovery Project, which is done out of McMoon's at NASA Ames. That's what it's called. So actually, there's pictures of this. I can't use any of them because they're from a professional photographer's Flickr account. I don't know what the legality of that is. But yeah, so they're taking pictures from the Lunar Orbiter, which was launched in the 60s for observing the moon, and they just got the pictures back to restore them.
Okay.
So he and Keith Cowing decide, hey, what if we could bring this thing back? What would it take? Because on March 2nd, gosh, I'm stuck in the past, man.
Stuck in the disco era.
I'm just stuck there, man. I gotta go out my hair, I get the sideburns. Oh, this is gonna be a disaster. So a dish in Bochum, Germany detects the signal, and this is it. This is the signal. So
Can't stop the signal, Mel.
Exactly. This is the carrier signal for ISEE-3. The rest of this is just noise.
Okay.
So it detects that signal. So to get the spacecraft to work again, here's what they need to do. One, work with the JPL Deep Space Network to get an accurate location and trajectory of the spacecraft, because the last time they got it was in 2008, right? That was 6 years ago. Two, figure out how to receive and decode telemetry data.
Okay.
Three, use this telemetry data to determine vehicle health and talk to the spacecraft. Yeah. So this is kind of what they're planning. So the plan is to restart ISEE-3 and perform a few burns to get the spacecraft back in heliocentric Earth orbit before keeping it in a HEO, throwing it back to L1, because, right, here's one of the options.
Gotta return it back. Return the spacecraft.
Yeah, you put it back, you pirate. Or toss it to Comet Win Rotten in 2018. This data collected from the spacecraft would be open for citizen science through an app or a website or something like that. They never got that far. So the reboot needs $125,000 for the basic goals and $150,000 for the stretch. And they get $159,500 by May 15th.
Yes.
I remember when this was happening, because this is 10 years ago. I remember when this was going on.
Yeah.
So the team... Oh, so here, of course, here it is coming back in, right? So it's going to do a lunar swing by. I'm going to use that swing by to capture.
Got it.
Oops. So the team builds an S-band transmitter on Arecibo, because that's a big dish, because it's 3 million miles out at this point. They need to talk to it, and none of the ground stations right now could talk to it, but Arecibo could. So what they have to do is build an S-band transmitter, because ISEE-3 operates on the S-band. And they used Arecibo to talk to it. The plan is to use the dish at Morehead State University in Kentucky for the rest of it, and the one in Germany.
Okay.
Does that make sense?
Yeah.
Okay. So this happens on May 19th, and I have pictures of this. So on May 21st, the project signs a Space Act agreement with NASA for technical support and recovery operations. Pretty much it's, hey, NASA, can you open up your file folders and find the technical documentation for how this thing works so we can use it? And then NASA goes, sure.
Yeah, let me dig out the old keys from the key ring to those lockers.
Let me check my Rolodex. Get one of the big skeleton keys too, like they use in those old houses, right?
Yeah.
Of course, the file cabinet's in the basement that's underwater. Okay, here it is. It's all in slabs for some reason.
It's somewhere in there. You find it. It's yours.
Yeah. So here's some of the options of what they're going to do, different trajectories, and how they're going to plan it out, right? They're very interesting looking, as you can see.
Big loop-de-loop scribbles.
Yeah, they could go to L2, right? They could go to L1. They could go to the Comet. So this is Arecibo.
Dang.
This is the team at Arecibo. So they're putting an S-band transmitter, I think, in here. Because this is the dish part of it, right? Because it's a satellite dish, right? Get the dish, which reflects out. Signal goes or in.
Yeah.
Right? So this is actually the TX. This is the transmitter line cabinet for it in Arecibo.
Okay.
This is from the blog of the guy who actually built this. This guy, actually. The reflection there.
Okay.
So look at all this technology. Signals, encoding, processing. If I knew anything about this subject, it'd be way more interesting. I'm sorry.
You should be.
Yeah. Dad, oh God, Dad's going to be so mad at me now. So this is the signal coming in from Arecibo, and you'll notice it's squiggly. Why do you think that is?
Yeah, at first I thought it was ISEE-3 doing a crazy Ivan, but it's spinning. It's spinning.
Exactly. That proves it's spinning, and it's actually spinning a bit slower, and we'll talk about that for a second. So now, what about data? I found the actual data encoding manual for this spacecraft, and it is caveman technology. It sends back a frame, right, of data, right? So it's got 128 possible frames, like bits of data coming in, and each of these is encoded to what is this piece of data for, right? Is this telemetry? Is this me saying, hey, I'm transmitting you data? Is this, from the plasma wave experiment? That's what this is pretty much saying, right?
Okay.
I actually got some of it. So it sends 8 bits in one word, right? So it's sending that in. So each of these, so the whole thing's like, I don't know, again, I don't know anything about computers or encoding or any of this. I spent so long reading through these things. This is just, I like orbital
Could make heads or tails of it, right?
Yeah. So I actually did take some of it, take one of the frames, or at least one of the rows of the frames, and turn it into binary. So this is that. Okay. This is what I did. Yeah. So this is about 128 bits. So it sent. So each of these like spots is a byte, which is 8 bits, or something like that.
Okay. Yes. And that is correct.
So so it's sending those back, and it's pretty much the problem is the encoding equipment to read these frames was destroyed. I guess they fed it to an alligator or something. And so this team actually had to build a software-defined radio to take the telemetry data in and then process it into something useful.
Got to translate it from whatever caveman technology it was sent in.
Right. They're taking their VHS tape and putting it on their computer without a VCR.
Okay.
Yeah.
Nice.
So here's a timeline. So first, on May 29th, they send commands to the spacecraft to put it into engineering mode. So it starts talking to them. Instead of saying, hey, I'm alive. Hey, I'm alive, right? So on June 26th, Goldstone, that's one of the dishes in the Deep Space Network, provides some communications with the spacecraft, right? It's a coordinated thing.
Okay.
On July 2nd, they fire up the thrusters for the first time since 1987, and this is actually the data accelerometer data coming back in. That's what this is.
Oh, wow. Oh, okay.
So they actually have to pulse them because it's spinning, right? So it's these little guys right here, these little thrusters.
Ah, okay.
Right,
these knob-looking guys.
Yeah. So it's spinning, they got to pulse them, also so they don't melt. So the spacecraft is actually spinning at 19.16 RPM instead of 19.75, and it's slowed due to the Yorp effect. You know what that is?
No.
Okay. It's first observed on asteroids. One side of an asteroid's hotter than the other. What happens?
So it heats one side heats up, and then it gets warmed up by the sun, and then it rotates, and then it cools off.
Close.
Right?
So it's rotating because of its heat. So remember, the hot side's giving off more light than the cold side, because it's hotter, right?
Mm-hmm.
Light doesn't have mass, but it has momentum. Yeah, so it gives off all these, and it's causing it to spin because it's lumpy. So the same thing's happening with ISEE-3. One side of it was hotter than the other, I guess.
Huh.
Yeah.
Oh, okay. So it's thermal kinetics.
Pretty much, yeah. It's called the Yorp effect because like 5 people discovered it. But it was first observed on asteroids because they noticed it would be spinning wrong, and they realized one side was hotter than the other, and so it was doing that. It's really interesting. So they're preparing. So by turning on the thrusters, they're preparing it for an actual maneuver on July 8th.
Okay.
This July 8th maneuver is to set up the August 10th lunar flyby to capture it into Earth orbit, and it's a delta V about 8 meters a second.
Okay, pretty small.
Yeah. It fails. So somewhere along the line, it lost all of its nitrogen pressurant. Right? So here's a diagram of this, right? Here's the nitrogen. There's hydrogen coming in from another tank.
Mm-hmm.
It lost all of its the pressurant. Don't know what happened to it. So they keep trying for the next few days. But
sorry, nothing. Continue.
Yeah, so somewhere along the line, maybe the nitrogen froze. No one knows exactly what happened, but it failed. So, on July 24th, the reboot team decides to shut down the propulsion system to save power for science equipment. And then 6 days later, they decide to make this the ISEE-3 Interplanetary Citizen Science Mission. Because only 5 of the experiments still work, they figured, okay, we'll get some science data from this thing, so we could get citizens to get involved. So on August 10th, it does a lunar flyby. Is that? Yep. At 18.4 thousand kilometers. It's about 11,000 miles. And this puts it onto a 451-day orbit at a semi-major axis of 1.1 AU. Now,
so it kicks out a little further.
And the problem with this is ISEE-3 wasn't really designed to go out that far. And it's got no battery. So at that point, on September 16th, they lose communication because the spacecraft enters safe mode. And communication is lost.
Ugh. Dude.
Now, depending on who you ask, in 2029 or 2031, ISEE-3 will return. But without Arecibo and without power, it's just going to be another object coming in.
Dang.
Yep.
That's tough.
That's ISEE-3. But the impact of ISEE-3 is pretty astounding. So this spacecraft here is Geotail, which would go to Earth's Geotail.
Geotail.
Which we used a double lunar swing by, which was validated on Highton Hagoromo, which we discussed last year, which used some of the ideas about L points and halo orbits to do its maneuvering, as we discussed last year.
Yeah.
Yeah. This is Wind, one of the 10 or so spacecraft that's gone to L1 since ISEE-3. And this is James Webb, which is one of like 4 spacecraft out at L2, using very similar halo orbits.
Yeah.
ISEE-3 paved the way for a lot of science missions.
Heck yeah.
And that's ISEE-3. I was going to use this image for the cover, but then I realized, oh no, spoiler alert down over here.
Yeah, makes sense.
This is one of my favorite science space missions, by the way.
Yeah, I mean, all of the orbital mechanics and...
Yeah, just look at all that.
did an enormous amount of loop-de-loops.
There's a lot of loop-de-loops. It is an incredible mission. And then, of course, the ability to bring it back and reboot it is just phenomenal. And the stuff I read of like the telemetry data and how they encoded certain things is just astounding. And caveman.
Yeah. And I mean, it would have been like fully, totally spectacular if we understood anything about what it was measuring to begin with.
The best understood stuff, the most important thing, the only reason we're here, dust counting. We got that. Don't worry.
Yep, we had that. Oh yeah, we had that. That dust was counted.
Yeah, and that's ISEE-3. It's such a cool mission. I really do like this. I like the spacecraft too. I mean, it looks cool, doesn't it?
Yeah.
Yeah. It's a phenomenal mission. And to think, again, it's way outlived its expectations. It did a lot more than it was ever supposed to do. Yeah. It's amazing. It's inspiring.
Yeah, Sorry.
Because I remember when this was happening 10 years ago, when they were bringing it back. Because we're at the anniversary of it, actually. This is the 20th. So this is around the time they were trying to diagnose the propulsion system. When this episode comes up, it'll be around August 10th. So,
dang.
This is such a cool mission. It is so interesting what they did. And just bringing it back. It's a shame they couldn't.
Yeah. Lost all the pressure, and that sucks.
The one thing I understand about these spacecraft, lost the pressure. It's all gone. Really cool order.
Lost it in Vegas.
Though. Yep. Disco Fever, man.
Yeah.
Yeah, so that's ISEE-3. You have any final thoughts on ISEE-3?
I mean, like you're saying, it's incredible, it's inspirational, and just seeing like the orbital mechanics that it's doing. And I know that like for us, the electron stuff was not all that interesting, but even seeing the plasmoids and like a diagram of the plasmoids from the information, and then seeing it be hijacked by pirates as the science team put it, to then go out and measure the dust of like Halley's Comet and and Hans Zimmer. Yeah, and then trying to see the efforts to bring it back. Like it's all inspiring. Like I got pumped when you started talking about like how the efforts to bring it back and recover it.
It is astounding.
Yeah, and just all of it. It is a fantastic and inspirational mission. Yeah,
it's really cool. It's a shame there's no other spacecraft we could really do this to.
Yeah, I mean, hey, first Comet flyby.
Yeah, a spacecraft that wasn't supposed to do that.
It's the first time for everything.
That there is. And it is also a testament to what these things can do, too. This is a spacecraft from 1977. They were able to wake back up and get operational for the most part.
In 2014,
way after it was supposed to. So, yeah. All right. So in the next episode, we're going to do STS-8, another early shuttle mission. And the spectacular part about this mission is that picture there. What do you think it is?
Is the guy riding the unicycle?
Yep. It's technically the second African American in space.
Oh, nice.
Yep. We're doing that next. Well, you want to play us out?
Yeah, I will. Until 2029 or 2031, this has been End of Mission.
Yar.